well, let's go ahead and get started. I reserve the right to change my mind, but people will continue to show up. The buses, it's a tricky day outside today, so I'm fine with it. And we have most of the teams represented here today, so that's also fine. If you take a look at Canvas, where this is kind of scheduled, it's right around this week, and I'm not as beholden to the deadlines for this, other than it has to all kind of get done by the end of the semester. But as I've mentioned a few times, after our typical like 2-week MP assignments end, and they're going to end not after this one, but after the one after that, we're going to spend the last few weeks of the semester working on these group projects. So let me just lay out, and I'll kind of read through, but just highlight the parts that I think are important for the basic parameters for this project. Preferably, although not strictly required, the concept is that you're going to be expanding upon some portion of the SGP design. So you can think of it, and I think the right frame of mind to have for this is going to be, we have all that we've built up through MP4, which is a little speculative, but you can take a look at the MP4 document as well and see what that includes. We'll assume that by the end of the MP4, we have our vertex shading, we have our fragment shading, and we have a decent amount of like the fragment render output operations that we talked about on Tuesday, the depth buffer and alpha blending and things like that. And then the right frame of mind I think to get into would be to think about, okay, what can I add on top of that? What is a reasonable extension of what is already provided by the time you are done as a team with that MP4? I know it's a little speculative, you haven't finished it yet, and you have to kind of think beyond what you'll have done at that point. I think that's still the best bet and the safest way to go about proposing a project. You also will potentially have the option, depending on the extent to which our board and our FPGA resources are filling up, you also have the option to kind of remove some things out of it as well. So since your project code won't be expected to have to run necessarily every program from MP1 through MP4 with the same fidelity it did back then, you have a little bit more flexibility to tear some things out and add in what you would have there. My expectation is it's going to have both hardware and software components. By significant, I think, in the same vein of what we already have for our existing MP assignments, that you have probably some new IP core. I think that'd be a likely thing that you'd be proposing, or some modification of the existing IP cores that are in there, and you'll have some new OpenGL functionality or some new graphics functionality you're going to be supporting, and you're going to have some software associated with that. A demo application, some driver code that you'll be changing. That's all I mean by significant. And again, I want you to have that frame of mind that that's kind of the scope for this sort of project, because there's a difference, right? With MP3, there's a lot of work to do. I think some of you are starting to see that after yesterday's lab, but it's scoped for you to get it done in that 2 weeks. Same for MP4. But now for your own project, it's kind of, since it's open-ended, there's a little bit more challenge associated with that. We'll have a bit of a review process of the project proposals, but ultimately, I have a decent feel for how challenging a particular project would be or otherwise, but I haven't done the projects myself, and so it is really kind of, an unknown with regards to that. In terms of the scope, you want to be more modest than trying to be more aggressive with regards to that. I feel like the teams are working pretty well so far this semester. I used to teach this class and senior design at the same time, and it was always funny that half the senior design teams were having problems and teammate problems and like wanting to split up and reform, and then these teams were always so nice and structured. Seems like things are going well, and you can just keep with your project team. If you'd like to change or combine your team or do other things flexible with the team, just talk with me first, and we can talk about that and see what would work best. But at least based on the MP2 demo day, I feel like the teams are doing very well. I'm very happy with the teamwork and what's coming out of it. Not everything is perfectly split 25, 25, 25, 25, but it appears, at least based on your own write-ups, to be close enough for my purposes at least. We're going to have, I list 3, I'm guessing we can be fine with just 2 presentation. So we will have a 5-minute kind of project presentation that you'll give on the proposal itself. I say Monday of week 10, that's technically, the week after we get back from spring break. We'll have some time in class to do that. I had this scheduled to have a 10-minute kind of project status presentation. I think you'll be busy enough. I may go around the room one day and just kind of ask teams how it's going. I don't think we'll require a formal presentation. But then what we'll have is a 20-minute kind of final demo day during our final exam time slot in finals week this semester. So a little 5-minute, here's what our project is about, kind of discussion among the class, then a final demo day like we've been doing, except now everyone's going to be quite different in terms of what their demo days are going to be looking like. Each project should be different. I think there's 4 teams. I don't want to see any kind of duplicate projects. I don't think it's necessary. So we can maybe post in the projects channel in Discord kind of laying early claim to an idea or speculatively claiming an idea. I think we can have 4 different projects with relatively minimal overlap. But conceptually at least, I expect the projects to have different scope, different technical focus area, different things you'll be working on. There won't be a single grading rubric for all of the projects. Instead, and I think this is probably the hardest part of the project proposal, especially if you don't have experience doing this for other project-based courses, I'm asking you in your teams to get together and think about what your own evaluation rubric could be for your project. If you look in Canvas for MP2 or MP3 submission, there's a rubric that I provide there. It's pretty high level because Canvas makes it a little difficult to have all the appropriate boxes, and so I make it pretty general. One for pre-lab, one for demo, one for the write-up, and one for technical completeness. Yours can follow something kind of similar to that, except you'll be able to provide a nice kind of 2-dimensional rubric, and I'll provide an example here on the second page, and we'll talk about it. In terms of how the grading will get done for it, I think it's nice to have a combination of peer as well as instructor evaluation. So 50% of your score will be based on my interpretation and evaluation of your rubric, and 50% based on what your peers think about your rubric. So during that final demo day, during final exam week, you'll give your presentation. I'll provide a little Qualtrics or other survey. Maybe I can do it in Canvas that you'll then go in for everyone else's projects but your own and provide your own feedback to them in your own team evaluation. This may be a source of stress for you, possibly, depending on your perspective of things. Your goal should be to make the rubric as concrete and minimizing as much vagueness as possible, so that it should be pretty obvious to everyone what the rubric evaluation is at the end of the day. There's certain words to avoid because they're really up to interpretation. Other really concrete goals you can set, and then while yes, 50% is based on student evaluation, 50% based on my evaluation, well, the peer evaluation gets kind of averaged out, so if there's outliers, that's fine. And then I think my evaluation should match very closely with what your own self-evaluation is at the end. In general, I want you to succeed in this and in all your classwork, but certainly for this project, I want you to create a rubric that you can get 100% on. And that's my goal for you, just like it is for the MP assignments as well. I know you're putting in effort, so why take off points if I don't have to for anything? Here's just some ideas. You have a lot of freedom with what to explore. There is still kind of that chicken and egg issue where we haven't learned a lot of advanced things yet. Every so often I drop a hint or two of what could be an interesting project idea. I'm also open to suggesting more ideas if none of these sound interesting to you. But I think as a team you can kind of decide what part of the labs have you been enjoying, what part of the labs do you not want to do ever again, what aspects of this class, like in-class content, did you want to learn more about, what parts did you not really care for, and maybe just kind of go for something that you think would keep your interest for that last part of the semester where we're working on it. All of these are fine. I'm always open to framework improvements, like what are some things that if you had in place when you worked on any of these particular assignments would have made life a lot easier, would have allowed you to progress faster, understand things faster. That's a little vague, but you can think about some things that would make sense. Any sort of OpenGL features we don't currently support are fair game. We just have to pick the right scope for what that would be. Texture mapping it's actually a specific example of that as an OpenGL feature that it's in MP4 document if you read that, but even in the MP4 document I kind of mentioned it's a stretch goal for MP4. Doing it properly probably takes a few more weeks, and so it's appropriate. We do have an embedded microblaze CPU in that SGP design. I use it just for some kind of self-debug sort of things, but we don't really use it for anything interesting. Having a boot-up screen, BIOS, ways of interfacing with the hardware, allowing that to be a built-in kind of testing mechanism for the design. The CPU, that microblaze has access to the entire address map in the system. In theory, You can run the code itself. You can run OpenGL itself on the microblaze, but working with that, and if you really enjoy the embedded software side of things, talked a little bit about anti-aliasing, rasterization of lines or triangles with anti-aliasing, performance improvements. That sounds better, but you really have to have a concrete idea of what that would mean in practice. I don't want you just to propose, we're going to make it faster. You have to have an understanding of bottlenecks as they currently exist in the system and some real, concrete ideas of how you potentially improve upon things. Deferred shading is something that a lot of the pieces are already in place, and we haven't talked about that concept yet. But at a high level, this was still something that is used quite a bit, but something that was much more popular back when we didn't have programmable shaders, which was setting up shading targets where we weren't actually rendering to a frame buffer, but instead we were rendering to a texture. And that would allow much more advanced kind of looking effects than what we could just do with traditional fixed function hardware. Those are just some examples, and the team really has to get together, maybe start throwing out ideas on Discord over spring break. Obviously discussing while you're waiting for a bit file to build. I mean, I think there's plenty of time to get this done without too much stress. There's a write-up aspect for it. I don't care about the write-up per se. I just want you to be thinking about it and then putting your thoughts on paper. So that's the point of the write-up. If you look at the Canvas submission for the project proposal, it's a 0-point submission. So you can't lose points on the submission, but I do want you to carefully think about it because it's only going to help you later on. Thinking about the issues now versus not fully thinking them through, and then once you get started on the project, realizing on day 2, oh, this idea is not really feasible for this particular reason. And I want us to avoid that because this rubric, once you submit it, once I hit approve, it's good to go. I'm going to hold you to that for the end of the semester. So I do want you to think carefully about it. I don't care about like the creative writing side of the exercise here. I care about showing your thought process of how you're going to be able to get this particular project done. With the structure of high-level overview, list of project goals, and being specific with those. What do we actually want to accomplish? Talk in terms of hardware, software, driver improvements you're going to be making. If it's possible, depending on the scope of the project, paint or other mock-up of what the end result could look like once you have it done. A high-level project timeline. It's got to be pretty high level given the relatively short amount of weeks we would have remaining. But I'd like to get a good feel for, okay, we have 3 or we have 4 team members. What is everyone going to be responsible for? How's it going to come together at the end? When we have an MP assignment, I have a pretty firm idea of what that would look like in practice just from putting it together myself and just prior years' experience. For these projects, I don't necessarily know how it all comes together. You do need to really think about that and kind of convince me it's all going to come together. And then finally, a grading rubric that you're going to be providing. So just a quick show of hands of the hundreds of us in class here today. How many of you have created your own rubric for a project before? Half. Okay, good. There's different philosophies on that. I like it. I like rubrics in general. I like assignments to have kind of a contract that when you submit an assignment, you should know exactly what grade you're going to get back out. Creating your own rubric is kind of necessary for something like this, but you can think of it as just a 2D table, and the rows on the table are the attributes. You can think of those as features, but they don't always necessarily correspond to particular features. In this case, several of them do. That's the rows, those are the attributes. The columns then would correspond to a proficiency and or performance scale. How well did we do on that particular attribute? And that gives you that kind of two-dimensional layout of stuff we hope to get done, major milestones or technical features. Here's what an okay job is. Here's what we want to get done. That's the middle column there. And then, hey, is there some extra thing we could have done if we had more time, or if we find that this particular feature is actually a lot easier than we thought. We can actually do more with it than we considered. The idea then for this class's rubric for these projects is, as this project is roughly meant to be 2x the difficulty of a typical MP assignment, you have roughly 2x the time to work on it. It should then add up to 200 points for a complete 100% submission and evaluation on this project. And so as we see here for this example, which would be a rubric if you were going to do lighting calculations, I kept this one in here. It's not really super valid. After MP3, you'll be able to do some lighting calculations. You just have to write the shader for it. But here we have the various features that would go into an implementation, and I would want you, of course, your features are going to look different for your project. I want you to use roughly those same 3 proficiency scales of level 1 is, you made some progress. Level 1 is not we did nothing. It's, we tried some things, but it didn't exactly work the way we wanted. Level 2 is your goal. Our goal is to hit level 2. We've done what we said we were going to do. And level 3 is, give yourself some bonus point opportunities in various different ways, so that just in case for one particular aspect of the project, it didn't go as well as that part of the team had hoped, it didn't quite come together, you lost some points even in your own evaluation, but this other part went really well and we got some bonus points, and then hopefully it all kind of evens out. Add your accomplished and or satisfactory level, that should add up to 200. So I think 4 attributes with 50 points each is the best way to do it. If you want something different within reason, that's fine. If you want 7 attributes, if you want 4 proficiency scales, but I want the middle column, we got stuff done that we claimed we were going to get done. I want that to add up to 200 with perhaps up to 300 points for, you got bonus for everything you wanted to do, and maybe closer to 100 for we made a lot of progress on these components, we didn't quite get them working. Again, that's not 0. 0 would be we didn't start on this part at all, we didn't do anything for it. So you can get less than unsatisfactory if you have no actual contribution for that part of the project. And again, I mentioned it here in the document as you reviewed that as a team. This is a 4-person or 3-person, 4-ish week project that you're working on. It's not senior design. It's not your master's thesis or creative component. Yet you have to scope it. So your job in coming up with this project proposal is not to impress me necessarily, right? It's to come up with something reasonable, hopefully fun too, but something that's not intractable over the period of time that you have here, and your rubric should represent that level of effort required. One thing I like to see, although it's possible your team doesn't have anything that would qualify here and you don't need to put it in your rubric, would be giving yourself credit for fixing relevant technical debt along the way. That one's obviously kind of vague, because what does that actually look like really is going to depend on your project, and you can make it a bit more specific. But as part of that, you do have to recognize at least up through MP3 the timelines will align where, okay, our MP3 didn't quite get done, or even our rasterizer still has a couple bugs in it. We have to fix that in order to actually succeed in this project. Or again, maybe you don't. Maybe you're going back to MP1 code base and only doing stuff with points, and that's potentially fine as well. But give yourself credit for fixing things that would allow you to actually make progress on your proposed part of the project. And then similarly for the other technical attributes for the project, as you'll be working on driver things, give yourself credit. As you'll be doing some kind of demo software, give yourself credit for it. And then for the hardware that you're going to have to build, make sure you give yourself credit for it. Any questions about project proposals?
I guess it's not about the proposal, but with the demo, are we also going to be writing like a written report for the...
That's a valid question. I'd have to check what I requested in Canvas. If there is a write-up, it's not anything significant for the final submission. We give a presentation for it, and as part of the presentation, there's like a self-evaluation of the rubric, and the only thing that would be required, well, I want to see your code for Canvas submission as well, so like your VHDL, your C code, and things you've added. The only write-up I would need would be if you want to provide more context for the evaluation of your rubric would be sufficient for that. We're already kind of at that point with the MP assignments. Not every team is the same, where some teams are putting a lot of their documentation in the slides and others are putting more and more of it in the write-up. I kind of want it all in the write-up because I can just look at the write-up and not have to look at the slides as well. But for this final demo day, as part of it, you are kind of self-grading yourself in the slides, and that'll be an important part. I don't expect there to be a write-up for this other than that initial write-up. But what I say here is correct, and the successful projects, the ones that have been really happy with the end results of their own project for this course, is those that kind of did a little bit of that groundwork. So this is not just a creative writing assignment. You can't just come up with an idea, write it up, and say you're done. You have to actually think through it. You may require some initial exploratory work of not doing the project in advance, but at least doing some maybe quick feasibility study. Is the concept valid? Are there some major roadblocks that you have to think through in order to be able to accomplish this project? So it's not a creative writing exercise. You're not getting graded on the proposal, but putting in that extra time up front, scoping things appropriately, not trying to impress anyone with your rubric, just be intellectually honest with it, something reasonable as well. That takes a little bit of time to do properly. So get started now, plant your flag for an idea that your team is interested in, and take the time required to do this part properly. Okay, switching contexts, and as I mentioned on Tuesday, I wanted to do this learning module before number 5, so that's a little backwards. MP3 requires knowledge of both to some extent. MP3, you're building programmable vertex shaders to do viewing transformations, but of the two topics, understanding the programmable shaders is much more important for MP3. We are doing transformations in MP3, but you can get 99% of the way there without really having a great feel for what's happening in that particular code. Whereas understanding what we're trying to do conceptually with shaders is pretty important for MP3. So I want to make sure at least covered some of that. So for the motivation is a little bit of what we already talked about when we talked about the evolution of OpenGL, which is why we advanced beyond just fixed function hardware. We talked about like the OpenGL 2.0 state machine, which was configurable state updates for hardware that is otherwise just doing the same thing over and over and over again. Kind of like our MP0 design, really good at doing one particular thing. You can maybe tweak it in a couple of ways to do the thing. You can change the matrix and do a couple of slightly different things, but the limited effects of what you can do with fixed function hardware led to renderings that look roughly similar to each other. Real systems we may want to model could have an infinite variety of the type of renders we'd want to do, the type of materials, the type of objects, the type of viewing, and there are approaches. In fact, you can see all sorts of just incredible looking effects done via fixed function hardware, but a lot of that is really done via kind of pre-processing and is kind of limited for real-time rendering as well. The major advance in real-time graphics is the concept of this programmable shader hardware. I mentioned shader refers to both the program that is executed and the underlying hardware that it's executed on. We have at the very least both vertex and fragment shaders. So the vertex shader is our program and the underlying hardware that computes the transformations typically required in that vertex or geometry processing stage. Right now, we don't have that until you build your MP3 hardware. We are taking our vertices and we're just kind of passing them through to the point we assemble them and build triangles out of them. This new hardware that goes in between the vertex fetch and the triangle rasterization and the primitive assembly is to be able to allow us to run somewhat arbitrary but also kind of constrained programs on those individual vertices, to transform them, to move them, to adjust any kind of attributes associated with them. That is what a vertex shader is, a program that modifies our vertices. Then there's also the fragment shader. That's a program that allows us to define and or modify the attributes of the fragment. That'd be post-rasterization, but pre-render output is where that module would go. We have a rasterizer, it's given a certain number of attributes, it interpolates all those attributes as it's told to interpolate. The end result is this fragment that has all these properties. At the very least position, XY here's, and XYZ as we see now, where this fragment is located in our screen space and in our depth buffer, and then potentially color attributes, potentially texture coordinates, whatever programmably specified attributes we need that fragment to have is present at that stage, and then the fragment shader then determines what to do with those attributes. Modify them, discard the fragment, do any kind of movement of that fragment potentially as well. In terms of the shader language, there's kind of an interesting history, but the end result is a series of shader languages that look roughly the same, even if they're technically different and not technically compatible with each other. In the early days, Cook and Perlin were developing languages for performing effectively what would now be referred to as shading calculations. If you've heard of RenderMan at Pixar, that is the underlying hardware, as well as the RenderMan shading language, which is still pretty much the language of choice for kind of non-interactive rendering. You can look up RenderMan shading language. We could build a course based on that as well. It's very similar to what we're doing here as well. One of the real early kind of available for just typical, workstation devices was CG, which you can maybe guess based on the name. That's C for graphics. The intent was kind of a platform neutral, also maybe card neutral programming environment. And then with the release of DirectX in kind of equivalence to CG, we had it in roughly that same time frame, the release of HLSL or HL slang and GLSL, which was for DirectX and kind of the closed source Microsoft way of doing things, and then the OpenGL way of doing things. And today, the use of GLSL and HLSL is quite prevalent. There's still quite a few platform-specific languages. So for Apple devices, you can use metal shading languages. There's still also PlayStation shading languages for PlayStation platform. That's for PlayStation 4 platform. But they are very similar to each other. So you may find, depending on what resources you're looking at, for open source games using DirectX, Direct3D, HLSL is probably more popular than GLSL. They're very similar to each other. You have to have the manual for each open to kind of do that translation, but there's all sorts of tools that also provide that auto translation as well. What the future is, well, it's kind of hard to speculate with any certainty, but if you look at these languages, as we'll see, they are C++-like languages, and they are all targeting an intermediate representation that is meant to be appropriate for the graphics driver to take and convert to the necessary microcode for the shader cores themselves. So the likelihood is the future is just some constrained subset of C++ would be sufficient for doing this kind of programming. And as we'll see, that's basically what we are already doing when we are using GLSL. We have to have an understanding of what's underneath the hood here. We're implementing the shader cores ourselves. We have to have some reasonable approximation of what that assembly interface would be. But in terms of the programmer's interface, A, the languages as they've evolved over time have a lot of similarities, and B, they're all kind of converging towards the same kind of intermediate target as well. It's usually easier to play with GLSL-like syntax using WebGL. So you're welcome to go to one of many type of online WebGL editors. It's a good example, at least this one that I picked, of the type of vertex and fragment shaders that we should generally be able to get working in our own hardware by the end of MP4. Also, just if you have Visual Studio Code, there's plugins to do basically a WebGL editor. And basically, this app as a plugin for Visual Studio Code works equally well. I like this one because it's not trying to do too much. There are plenty of examples of WebGL editors that basically cause my whole system to lock up because they're trying to really show like all the capabilities of it. This one is more so just kind of showing it at a high level what a shader can look like. It's also kind of configurable without having to worry about the rest of, in this case, JavaScript code that would have to go with getting a shader up and running. So this takes a texture that gets loaded, maps it to a cube object. That all happens outside of the code we see here. And then what is happening in the shader code is both the vertex shader, which is just going to be doing a transformation of the type we'll hear about, as well as some lighting calculation as well. So if we wanted to, we can both configure this, we can also mess with it quite a bit. We have, if we want to not map it to just a cube, we can play around with this one and map it to a very common model used in testing out 3D computer graphics, the Utah teapot. We showed a few examples of those back in the first lecture. You can also map it to a model of a 3D head. Looks a little creepy though, I don't know, having the WebGL logo mapped to someone's head. So let's go back to the teapot, I feel better about that. And you also can turn off some of the depth related and clipping and culling things and blending that we've talked about. That's not going to look as good with a black background. And then you can also just go and dynamically just modify what's happening in the shader. This is doing a type of transformation that we will talk about in the viewing transformations and lighting. But what it's doing is it's calculating a distance from a light source, and it's a hard-coded light source. I should be able to change this, and it should update, if not instantaneously, very quickly, of where the light may be located. I think it's going to be subtle, though, because there's no shadows. It's got a black background here. If it changed, I didn't see it different. Let me go back to a cube, and no, I guess we have to have it rotating here. That's the intensity of the light. It's white light, we could change it to, red light. Or if it's changing, the issue is quite subtle to me. Let me, instead of texturing, as we set the color, commenting that out should turn the whole thing off entirely. Okay, that's right. The actual output fragment color, syntax errors are great, should be, well, whatever we want it to be. I mean, if we want the whole thing to be, not enough data because I need diffuse is just a float. Okay, so that at least we can see the lighting. When we're doing the texture mapping, it's overwriting and it's a black background, it's kind of hard to see the lighting. That should allow us to change where the lighting source is coming from. We should be able to see this lit in slightly different ways, although it is, but it's kind of subtle. You can see that the light source moved in terms of where it's located in the scene, and then the diffuse reactions. We will get there. We will talk about that. This is just an example of playing around with vertex and fragment shader code to get different kind of looking effects. We can mess around with. Right now, the vertex shader is actually quite similar to one of the ones you'll be implementing for MP3. It's doing the so-called model view projection transformation. It's like your MP0 logic. It's setting up a matrix, and it's multiplying each XYZ value effectively by that matrix, and that allows us to modify what's happening here. We don't see the values of this because that would be the OpenGL code that would be setting up that matrix and configuring for it. There's a cube flyby example for MP3 that's doing exactly the same thing, just with a cube and not with a teapot here. We can mess around with it though. So that's GL position. We can keep modifying it still. Let's make, yes, it's going to keep complaining. Can I convert from constant int? Okay. Well, always having the x be 0 is going to be a problem. Because no matter what, each vertex would be at x equals y. That shouldn't break it. Okay, so we can modify it, right? And you can modify it. And so what's important to think about when we think about shaders as being applied to our vertices? Although, again, this is a nice tool, and any kind of WebGL editor is useful for that. We don't see the OpenGL code here, but what we don't do is recompile the OpenGL code. The OpenGL code hasn't changed at all here. We didn't change the input geometry at all. Our vertex buffer objects are exactly the same. Whatever the coordinates are for the teapot are exactly the same as they're inputted. What's now happening here is after we've fetched all the vertices, or as we're fetching all the vertices, we're streaming them through this piece of hardware or software implementation in JavaScript in the Chrome browser here, and it is applying some program to each vertex as they come through. In this case, it took a while to get something that didn't look awful, but we're saying do the transformation that was already planning on happening, and now take the x coordinate of every vertex as it comes through and modify it by 0.5. And let's make the y 2.5 or something like that. Okay, so we get our tall, skinny teapot here. That's happening after we're doing the fetching, right? So these vertices are fetched. Usually there'd be very little processing happening before this stage. They're fetched in and then executed typically with some sort of parallelism, and this program is getting executed on every single vertex before it goes to all the rest of the hardware you've been working on, which still by and large exists in modern GPUs. There's still going to be rasterization hardware. There's all sorts of attempts of trying to do, even in modern GPUs, like software rasterizers. But for the most part, given how critical that operation is, it's still a piece of fixed function hardware that are implemented. After the rasterizer, then you have a series of these fragments. And it depends. Oftentimes there's more fragments per vertex, but there's some ratio of fragments to vertices. And that's a separate program that gets executed on it. I was just trying to do something that was more interested in, once you apply the texture map, maybe for that particular texture, it's a little hard to see the lighting calculation. It's there. You can kind of see a little bit of a shadow on the left-hand side. So I just commented that what I said here is, given a light direction, so it'll be a direction from a light source, calculate, this is a diffuse lighting calculation here. We will learn this. Again, you get a feel for a little bit of the syntax. For the type of operations we typically would want to be able to support, there is a GLSL call that do exactly that. I want to normalize the input normal, usually be already normalized, but I want to do a dot product between the normal coming off my geometry, the surface normal of that particular triangle, and where that light source is currently located. I want to do a dot product of it. I want to make sure the value is actually positive, so I'm going to do a max of 0.0 and that dot product of the surface normal and the light. That gives me a relative intensity of how close am I to facing the light. Am I directly aligned with the light? I'll get a value of 1.0. Am I at a 90-degree angle from that light? I'm going to get a 0. And if, of course, I'm facing away from the light, I get something negative, but here I'm going to clamp that to be 0.0. That's diffuse lighting. We'll talk about a little bit more of the math behind that. And all I said here was I want to set the output fragment color independent of any texture here. I'm just going to set it to be whatever that value was, the intensity of the light reflection for both the RGB component that we have here. And we could say, like, instead of that, we could still do this. It's going to look pink, and now it's going to look red, where we're just going to set the red channel based on that, and the rest of them are going to be sent to 0. But what this doesn't require is recompiling our actual OpenGL application here, right? Now, this is some sort of editor, live editor, so as part of it, usually there's a process to actually load the shader, to compile the shader. If you're ever loading up an intense 3D video game, you'll see there's a lot of that load time that's loading textures and other objects and assets, but it's also usually compiling the shaders for your particular platform as well. This is one shader, one vertex fragment shader. Typical game could have hundreds of different shaders for different effects that they're trying to create. Long story short, that you can always play around with that to kind of see the kind of vertex and fragment shaders we should be able to support in our own hardware. There's many of these kind of examples online, but a lot of them are trying to show really advanced effects, which conceptually we could also support, but in practice, every new one of those instructions we would have to be able to support. Another way to think about that is, there's a normalization operation. So what does it mean? We have a vector, and we want to make sure it has unit length at the end of the day. So you have to take the intensity of the x, y, and z components that we would have here and divide by the length, right? So we could do that. We would just have to have hardware of our own that we implement to actually do that for us, right? We would have to either have a single unit that can do normalized operation, or we'd have to assemble that down effectively into micro operations to do the additions and the division operation, for us as well. Generally, although it's not a requirement, generally what you find in modern shading hardware is for every GLSL or HLSL or other kind of built-in language feature, there tends to be an instruction or just a very small set of instructions to implement that for you. I can't say it for a fact, but I can almost guarantee you there's a normalize instruction in modern hardware. There's a dot product instruction in normal hardware. There's a max instruction in normal hardware. We're limited by time and FPGA resources more than anything else, right? In terms of you could implement each of those. Each of those would take some time to build and test. We pick a reasonable subset for our MP3 assignment, and then there's a series of other ones that are listed, but are listed with an asterisk, and that's what that asterisk means in the write-up for MP3. It would be nice if you could implement those, but each of those is going to take a couple days, and so there's only so much time available to build these. You can do things that don't look quite as correct, but for example, if I didn't have the max operator working, we're going to have to change that real quick. Yep. If I didn't have the max operator working, I could get rid of it. It's going to look a little weird. Here it's just clamping on colors. It actually looks just fine for this. If I didn't have normalization, because that's hard, What could I do if I didn't have normalization supported? I could take, what would be the best way to do that? N divided by n dot x or something like that. N divided by n dot x. I need a single scalar value here. We can just take, no, that wouldn't work. Let's do z for how far away it is in that dimension. Dot, there's just a missing parenthesis. Let's go to n dot x, which is what I was originally trying. I had a syntax error. And it's not correct. Well, what's happening here as when x flips over from greater than 0 to 0, there's a really kind of stark effect there. Okay, but if that's all your hardware supports, I mean, it's better than nothing, right, for kind of building those kind of graphics effects. We're definitely, when we're working on our own shader hardware, going to be in the realm of compromise of what kind of effects can we reasonably build in a reasonable amount of time. And that's also just a valid place for project ideas where NP3 requires you to do this relatively small subset of the ISA, NP4 requires a bit more, and you may find for this effect that I would really love to see working in hardware, either it's in the ISA that we provide and it's not we didn't build it yet, or it's not even in the ISA and we'd like to be the ones who build it. I'm all for it. That's a perfectly valid project idea. The only thing you have to kind of watch out for is that if you're proposing something new in the shader ISA, it's on you, and you have to give yourself points for it to work on the compiler side as well. So some code still has to take this and generate the assembly. That code's in place, but you would have to add to that code in the driver to get that to work. Unifying stream between the vertex and the fragment shader is this concept of stream. The vertices are streamed in through the vertex shader. Post-rasterization, the fragments are streamed into each of the fragment shaders. And we typically think of this mode of computing as just stream computing or just streaming computing, where there's very little to no state associated with the individual computation. It's a little hard to see just looking at the source code that that's happening. There is some state. There's going to be some, let's look at the vertex shader. I think it's a little bit easier to think of it that way. There is going to be some per render state associated with the vertex shader and the fragment shader. The exact keyword we use really depends on which version of OpenGLSL we're using, but uniform's the right name for it, conceptually what we're doing here. Why is it called uniform? I guess because it's not varying from shader to shader as it's executing. It's uniform across all the calls to that shader as the vertices themselves are potentially varying here. But those are input attributes. These are things that are constant across each call. But in general, as we're executing this program, you can think of it as kind of like a one-shot, like an asynchronous call that just takes an input, consumes it, generates an output. Doesn't necessarily care or is even aware of any of the other processing that's going on in the system. Isn't aware of processing, for the most part, from one vertex to the next vertex. Same with our fragments as well. It's effectively executing all the vertices and fragments in parallel with each other with no real coordination between them. We do know that as we process the vertices, ultimately there is coordination because we take those three vertices, we assemble them into a triangle. But individually on a vertex by vertex basis, there's essentially no state associated with that other than the per render state we provide for things like input parameters here. That allows us to think of the GPU as a highly parallel stream processor because that is what it really is. So some of the terminology you will hear used is the stream being just the sequence of data. That's our input that we consume and as well as the output that we produce here. And the individual code that also is the shader is also referred to as a kernel of our computation. So the kernel, which you'll hear much more in the context of GPU compute, when you look at CUDA documentation, for example, the kernel is what is the individual program that runs on each element of that stream, generating some output stream. And this is just kind of an arbitrary view of a stream of data happening, but at the very least we have data streaming in. We're processing one block of that data at a time, the kernel being the program that gets invoked from beginning to end. So it's not like it's in a loop and conceptually there's a scheduling loop, but individually for each kernel, we have a start, we do our processing, we generate our output, we're done. We then go back to the beginning. input streams in, kernel does its work, output streams out, and then that then gets potentially connected to some next kernel for what we want to do in the next stage. Well, although we do have function calls and things like that in GLSL now, our best view of what would be happening in the GPU side would be we have one of these kernels corresponding to our vertex shading we want to do, and some more fixed function hardware kind of in between, and then a separate kernel doing our fragment shading after the fact. Where they actually execute is highly dependent on what type of GPU you're looking at. This is one of kind of the early programmable GPUs where they were physically distributed the hardware for doing vertex shading and fragment shading. We had a version of this picture kind of in the first week of the semester, but now as we look at it, maybe we can start to look at it and see how close it is to what we're actually building in class. There's a couple things that aren't being shown here and a couple things that we haven't touched upon as much, but up here, this is where your vertex shaders would be. Both the physical hardware as well as the program that's being executed. And on this generation of hardware before we had unified shader architecture, they were physically separate from each other. So you would have a certain number of vertex shaders, then you would have what is ultimately going to be a piece of scheduling hardware, but also would include the actual rasterization hardware here, and then you'd have a series of those fragment shaders then as well. So this view is conceptual of stream, kernel to kernel. Same exact thing is ultimately happening here. We stream in vertices, so it's not showing vertex fetch, so there's vertex setup that has to be here, but effectively we have that hardware in place already. We stream on our vertices, we do whatever that shader program is expecting, we then have fixed function hardware that does the rasterization, then we're streaming in our fragments from input to output, and here would be our render output core or cores, also doing a lot of the texture fetching and things like that potentially here as well. Main difference between this view of what's happening and what we are building in class is given our limited hardware capacity and limited student capacity, we're just going to have one of each. We're going to have one vertex shader in MP3. We're going to have one fragment shader in MP4. The end result is a very slow GPU, but it should still be correct in terms of generating the same result of that Kick.js example with WebGL. Should be able to generate the same exact result. So it's not a functional correctness issue, it's just a performance issue. If you'd like to look at parallel shaders, that should also be possible. My thought would be it's easier probably to do parallel fragment shaders than parallel vertex shaders, because then you do have a trickier scheduling issue of making sure all the vertices get reordered the way they need to be to do primitive assembly and the like. But you should have enough resources that once you have an MP4 fragment shader in place for your project, let's look at having 4 of them. That's a very common arrangement of doing a 2x2 grid of fragments at a given time. You would then just need to have something a little more complicated than what we have for this line right here, which is just a FIFO. And it would need to be something more complicated than that because someone has to now schedule the fragments to the individual fragment shaders. It may be 4 FIFOs. There has to be something more complicated than what we have for that here. But otherwise, while we haven't built all this yet, this is effectively what we are building this semester and what we're getting to by the end of this semester. What has changed, as we showed very early in the semester, is that now we have unified shader architectures. The main difference there is the recognizing that what is going on in here architecturally is extremely similar to what's going on in here. There are some subtle differences. There's some things that you only do in a vertex shader and some things you only do in a fragment shader, but there's like a 90% overlap of the type of math, the type of operations, the arithmetic and other things that are happening there. So while here it's still kind of physically separated into physical vertex shaders and physical fragment shaders, and for our lab we're also doing them physically separate, the recognition is that, well, they're doing so much of the same thing. Just have this one large pool of these shaders, these cores, and then just make sure we're very careful with how we're assigning work to them. That sometimes they're doing vertex shading, other times they're doing fragment shading, and now later on, now they're doing compute shading, and we're just managing the work associated with them. We don't really need to have it physically separate, because there's downsides of physically separating it as well, right? Here, this example has 6 vertex shaders, and if I recall, it's like 14 fragment shaders. That is a static design decision that once you've made for this particular chip, you can't unmake it. You can't change it. For certain scenes, that might be the right exact balance of fragment shaders to vertex shaders, but for other scenes, that might be really terrible, right? You may have your entire scene just be one big triangle that you're applying a lot of textures to, in which case, all of these units will be incredibly busy, and these units won't have any work to do at all, because they have very few vertices. So that's the other advantage of why there's now unified shaders versus these separate shaders, is because we don't necessarily know in advance at architectural design time what the right balance is going to be between the various shading tasks we may have. For our lab infrastructure, we could have done unified shading, but then this whole scheduling of work would have become a much more difficult problem for us to solve versus we still really have a top-down, left-to-right pipeline of the work that we are scheduling, and that works pretty well still for what we're trying to do. So let's talk a little bit about the shader mechanics. I think as seniors or graduate students are close enough to either, I think you'll be able to figure it out. So I hate to dismiss it all, and we'll cover some of the shader mechanics. We'll learn about it through some examples here, but I don't think there's anything particularly scary here. You can't go into shader programming and expect to write arbitrary programs because there are still, if not language restrictions on what is possible, it's not just coding in C or C++. There's significant performance pitfalls if you just try to do arbitrary programs using your shaders. But for the most part, syntactically, it does what you hope it would do. So the data types are typically going to be floats as a built-in data type, as well as vectors and or matrices of floats. It's a very nice feature of shader languages that you don't have to compose your own arrays. You don't have to build your own vectorized or matrix types. They're kind of built in as first-class citizens of the language. You also have types for arrays. And then the fundamental three different types of data that you're dealing with are your per instant data, your per pixel interpolated data, and your uniforms, your per batch data. And you do have to be very clear with regards to your shading code and your entire render that you're working on that it's very clear which is which. Another way to say this would be per instance data, vertex attributes that we're specifying. Our lab infrastructure is limited. We have 4 attributes. Position has got to be 1, color's got to be the other 2, so we have 2 more we can play with. So we don't have a ton of infinite freedom, but you look at a large number of vertex shaders and they make very similar assumptions. So we're not too far afield from what's possible. Then you have what that Kick.js example was calling varying data, and now it's just a shader outputs. That's going to be your per fragment interpolated data. That's what is going to be generated as an input to the fragment shader from our rasterizer. So vertex gets its input attributes, rasterizer then generates, could be a completely different set of attributes that is going to be created by the rasterizer. You can think of it in terms of the syntactical names, although this is definitely where the version of OpenGL and GLSL you're supporting makes it significantly different. But I just want to make sure, just for at least for this example, what we potentially have here. These are our 4 attributes for this shader. Vertex could have just been called position, so it's kind of ambiguous, but that's just our position. So maybe position would have been a better name than like vertex. That's my XYZ associated with each vertex as we specify it. We then also have the vertex normal. We'll talk about normals, and it's the same geometric definition that you would have learned in a math class, but that is also specified here. This one is not all that clear, but that's going to be a texture coordinate associated with each vertex, and then some potentially other information we can use here associated with it as well. That is our per vertex input data. In OpenGL, you specify that vertex buffer objects, you pass that data in when you do your render. Then there's this per, I'm going to use the same term on the slide here, per batch data, per frame data, whatever you want to call it. This is going to be uniform across all the different vertices that you have here. So each vertex will potentially have a different set of attributes, as they do now in your implementation, but then the shader will have also access to this other block of data. You can think of it as a constant. It's kind of constant. It's constant per run. That if you have 5,000 vertices in your scene, they're all going to have potentially different values for these vectors, but they will have the same value for these data variables in their program. This is what you're specifying as the programmer in your OpenGL to allow you to do different things from frame to frame here. And then while we don't use this keyword, we just use input and output keywords in modern GLSL, here is going to be what we are generating as an output of this kernel. And it's just given here, we're going to generate an output texture coordinate. It's called UV for historical reasons. We could have called it text coord. And we're going to also generate an output normal as well. Where it gets a little messy and where the syntax is just, when you Google it, you just have to be careful. What is the exact version of OpenGL and GLSL that I'm looking at, because the syntax has consistently been tweaked from year to year, is there's also kind of a hidden output varying type here that your shader is required to generate, and that's called GL position here. That is the output position of that vertex. So it's kind of a hidden, requirement, or it's not obvious in looking at the code that it's a requirement, that your vertex shader, at the very least, has to generate an output position, but then you have the option of having it generate other stuff, other output attributes. These are input attributes for the vertex. These, as well as position, are our output attributes from that vertex. So again, going back to that stream model, it doesn't have to be necessarily a one-to-one relationship. You can have one vertex attribute as an input and 4 vertex attributes as an output, or vice versa. Vertex shaders are required to generate something per vertex. At the very least, they have to generate the XYZ location of where that vertex needs to be, but there's no requirement that you have to pass all the things through. You can use it as input data and calculate something completely different as our output data. If we go back to a working fragment shader, just to make it look a little bit different, what would be the best way to show it? This connection of input to output is what's really kind of critical here. So again, there's input attributes, that's what's listed here on the slide as per instance data. There's then the vertex shader outputs, called here interpolated data. That is data that's going to the attributes that are going to your rasterizer, triangle setup attributes. Those don't have to be the same. Position is usually you provide an XYZ value, and usually you provide an output XYZ value. So that's usually the same, but there's no requirement otherwise that there's a matching, between the two. That is going to be your rasterizer output data, and then that then becomes input to your fragment shader. And we just have to be a little careful with how we do the plumbing between it here. Again, this shader has that GL position as output. It's also passing texture coordinates as that normal. That normal isn't really doing very much. If we were to comment it out, that's going to give us a problem if we're not careful. Yes, that equals, the normal here should be something arbitrary. And now we have a very flat shader where the whole thing has got the same normal no matter what the vertex is here. Now when we look at the fragment shader here, it depends on the version of OpenGL you're using. Here, the way it works and the way the compiler plumbing kind of makes it work is that we have the same name for the input to our fragment shader as we have for the output of our vertex shader. Modern OpenGL does not require that. We just have to be very specific about what location each varying or each input and output is going to correspond to here. In this case, if I were to call this N, might be easier to change it here. If I were to call this N2, it's not going to work anymore. We're generating an output, and this compile error is intentional. We're going to generate an output attribute called N2. Fragment shader is expecting an input attribute called N, and actually at the time of OpenGL, not the application compile, but running the GL compile shader type call. GL link shader is the one that would catch this. It should detect, call this varying output this. You're expecting this varying output called this. They're not the same. In this version of WebGL, it does it by name. In more recent examples of both WebGL as well as just GLSL, it does it by position, where we're saying this attribute is position 3, and then this attribute is position 4. And you can call them whatever you want, but just recognizing that position 3 of our output of our vertex shader is going to become position 3 of our input of our fragment shader here. So there's 3 types of data that we have to kind of keep track of. You can get very far with very kind of basic kind of things here. Let me show that one of the examples. I want to make sure we get to that, of the cube flyby. Has anyone played around with this yet for MP3? Just saw that it worked. This is a non-textured cube because we don't have texture mapping working yet. I think it was just arbitrarily chosen RGB components. And I guess the nice thing about it being arbitrarily chosen RGB attributes here is you can really see the triangles, right? I mean, it's very clear it's a cube that's made of the triangles that are each of the faces. And as you play around with this program, what it allows you to do is just use the keyboard to kind of change aspects of that vertex shader transformation. I don't remember all of them, like plus and minus and things like that. So there are 3 components then to that program, which in the past we were just really worrying about one component of that program. There's still the OpenGL code, so that hasn't changed. If you were to look at this OpenGL program for MP3, a large part of it is exactly what we've already been doing. We have a vertex buffer. In this case, there's more of them because there's the 6 sides, and each of the 6 sides are 2 triangles. So there's more of these locations than there were before. So 6 times 2 times 3, there should be 36 of these things in here. I'm guessing that that's correct. So 36 vertices we have to specify, but otherwise it's the same as the red triangle. And that's position information. The way we've been doing things, we've been specifying color information separately from position information, so we also have an equivalent sized array for color information as well. We do all the same plumbing for that aspect we've been doing before of gen buffers, bind buffers, buffer data for both those buffers. We are now specifying, although we've been doing this in our prior programs, that input 0 is going to correspond to our vertex buffer, input 1 is going to correspond to our color buffer, and then our draw call is actually nothing special. We're doing our depth buffer for our Z depth. Your program will not, or excuse me, your hardware will not be able to implement this as of yet. It should actually still look okay because we're setting up the camera so that we're kind of hiding what's in back. It'll still look like a cube, but maybe won't look exactly correct. And it's just calling GL draw arrays each time. So this program is exactly the same as the red triangle, just for additional triangles here, right? What has changed and what is different is our shaders are no longer those pass-through shaders. I believe, we have this little helper function that does the compilation. It's still pass-through on the fragment side, but on the vertex side, it's this so-called MVP transform. Here, the syntax looks a little different than in that WebGL example. They are different frameworks. Here, the name of it is whatever we want to name it for our shader, and we're being much more explicit. We're saying, we're going to lay this out at location 0. We're going to call something as an input vector 3, vertex position in model space. So that's location. That's our vertex location. That is the more modern way of doing what is specified here as attribute vec3 vertex. Be a little careful when you Google these things and look for examples that it's very clear what version of shader language you're using because it has changed. That is an equivalent thing that we have here. This is my first attribute. It's a vec3, and it's my position. Here, I'm being much more explicit and saying my first attribute, we don't use the attribute keyword anymore. We just use input. Same concept. It's coming into our vertex shader, and it's a vec3 called vertex position model space. And in this case, we have a second attribute called color here. And unlike this shader where we specify these varying types, for us, we're just specifying we have an output type that we're going to call vColor. We just want to call it something different to disambiguate it in our code. Our uniforms are those values that are going to stay constant for the whole render, for the entire time we're here. In this case, the one uniform we're specifying is a mat4, as we'll look at a 4x4 matrix, and it's called our MVP for model view projection matrix here. In terms of the math that the shader is doing, it's doing an MP0 style matrix vector multiplication. take the value of XYZ, concatenate 1 for that fourth parameter W here, take that as a length 4 vector and do a matrix, 4 by 4 times 4 by 1 matrix vector multiplication. Here we're doing some manual perspective division. I think it'll look good if we don't do that. Let's find out. Looks fine to me. But it's there in case we need it. And then for now, for our color, we're not doing anything with it. Just pass through the color. Again, you can mess with the color. You could say, give me color.r, color.r, and color.r. Still going to look okay because it's different shades of red, but it's going to look gray here, right? It's going to you still see the triangles, but you miss all the other fun color that we have here. That is our vertex shader here. And we still need now to associate one additional thing, not just compiling the shader, but the main difference now is we have to associate this value in our OpenGL code to our shader code here. And the way we do that is there's a two-step process. First, and it's kind of a manual way of doing it, we have to kind of query our own shader program that has been compiled and is set to say, let me know and give me a handle for that variable name called MVP in my program. This means we can't directly and easily, instantaneously divorce our shader variables from our OpenGL code as easily as we would like to. If I were to change this to MVP2, the shader is now syntactically correct. Is still, excuse me, syntactically correct, but this should not work. We have this call. Location's kind of a fuzzy word. Give me some sort of handle so that I can update that uniform in my code later on. We have, for this case, because we have a little keyboard interface, we want to actually then, when a key press, we want to change some parameters associated with where the camera is located in the scene, and then we're going to call this function called setViewingMatrix. This is using a separate library called GLM, and it's a third-party library. It's not part of the OpenGL standard, but when you use this library, you'll find that the stuff you're doing in your shader has direct correlation to stuff you use in your program. You're not required to use it. It makes your life a lot easier because it has support for the same kind of types that our GL shader is expecting from us. So here I'm setting a camera location in terms of where it's going to be located and looking at. There's functions that are equivalent to old school fixed function helper functions that say, set up my camera, have it looking at this location, and then also apply this particular transformation. The end result is a matrix, and it's actually two matrices that I can then multiply by each other, and then the call is update that matrix in my vertex shader memory for this next set of calls to my shader with that particular value given to by the pointer to, I can just, I don't know why I did that. I can just pass MVP. MVP is a GLM mat4. Maybe I have to do a raw pointer. We'll keep it as it is. Update that location in memory on the GPU side with the values corresponding to that thing generated on the software side, on the application side. This is an unnecessary helper function. I could have manually just created an MVP matrix, in C and just set it to whatever mathematical output I thought was interesting. You can manually construct it, or I can just use those built-in functions. The point of which we'll be learning more and more about all of that processing happens on the CPU side. Then when it comes time to actually do the transformation, this input is then provided for each frame. And as we change our keystrokes here, all we're changing are where the camera is located in the X, Y, or Z location. And we're just moving the camera around. And the shader is doing the same exact math each time, just with a different value for that uniform that we have here. As you look, and this will be the last thing I leave you with here, as you look at the other MP3 applications, Shapeshifter is definitely the equivalent of the red pixel or the red triangle for MP3. If you get any applications working, it should basically be this one is the main one to get working. Looks a little glitchy on my end, but I think This is a remote desktop connection and connected to a monitor and a screen. I think the glitchiness is on my side, not on the program side. This is the red triangle, but then the main difference is we specify a red triangle. I think we technically specify, I don't have the OpenGL open, a smaller red triangle to start, but then what happens in our program is we have a set of simpler uniforms to determine where we want to potentially move and or scale the vertex attributes for the red triangle. Give me my input position, which is just the XYZ provided in the red triangle equivalent application. Multiply X by a scale, multiply Y by a scale, and then give me a plus or minus X offset and Y offset. Again, I could also change the color in here if I wanted to. We get a very gray or white kind of triangle. This is an easier example to work with because it's all scalar values. As opposed to worrying about VEC4 values or MAT4 values, these are just individual floats. The calls to those GL uniforms are extremely similar. Your program then is going to take the assembly equivalent of this, which is basically load a bunch of things in off of the FIFO, do some multiplication and addition, so really technically that's all you have to get working for at least for this particular demo, and then do the out FIFO instructions as well. It's still tricky though. This is not a trivial program. These are data values. They're going to be located in memory. You're going to have a data cache to read from them. They're going to be changing from frame to frame, so you have to be aware of when you have to flush the cache and make sure you have the correct values there. But this is our red triangle example. I think all teams should be able to get this working for MP3. Guess we have to leave things here for today. So good luck. Discuss with your team over spring break what kind of project you may want to work on. And we'll pick up right here when we get back after break. Thanks.